Section 2.2 is limits and continuity, and I know you've done some work with limits already. So finite limits as x approaches positive or negative infinity. And you don't need to write all this down as long as you understand. The symbol for infinity does not does not represent a real number. We use infinity to describe the behavior of a function when the values in its domain or range outgrow all finite bounds. For example, when we say the limit of f as x approaches infinity, we mean the limit of the function as the x value moves increasingly far to the right on the number line. When we say the limit of x as x approaches negative infinity, that's moving to the far left of the number line. So, horizontal asymptote, this is our limit. The line y equals b is a horizontal asymptote of the graph of a function, y equals f of x, if either the limit as we approach infinity is b, or the limit as we approach negative infinity is b. In other words, when we have a graph and we have a line at y equals b, some horizontal line, and I apologize, this stylus is not great. I will do the best I can. That's supposed to say y equals b. Then we know that as x goes towards positive infinity, and or, it doesn't both have to be true, but it could also go towards negative infinity, the line y equals b is my horizontal asymptote. Okay, so here's an example. We're going to use a graph and tables to find the limit of f of x as x approaches infinity. Make sure you know how to read this properly. The limit of f of x as x approaches infinity, and the limit of f of x as x approaches negative infinity. So we're going to identify all the horizontal asymptotes of this given function. So let's look at a graph first. Oh, I think the graph comes up later. Let's see what happens. Oops, sorry. All right, so let's go ahead right up to here and then get your graph written down. So this is the graph of x plus 1 over x. Horizontal asymptotes. If we look at this graph, it appears that there is a horizontal asymptote at y equals 1. So the limit as x approaches infinity of this function as the function goes further and further to the right is 1. The limit as it approaches negative infinity going to the left is also 1. And our horizontal asymptote is the line y equals 1. Looking at a table of values, we also see that as we make our negative numbers bigger and bigger, we are approaching 1. And as my positive numbers get bigger and bigger, we're also approaching 1. Notice that on the left we are approaching 1 from the bottom, smaller numbers going up towards 1, and on the right we have larger numbers going down towards 1, and that mirrors our graph as well. So the sandwich theorem, we did not talk a lot about this, but a sandwich theorem is useful for functions like this, and it will pop up now and then. We'll talk about it as it comes up. But this particular limit, cos of x over x, we know that cos of x fluctuates between plus and minus 1. So the numerator of this is never going to be less than negative 1, nor is it going to be greater than positive 1. So the limit of this function as x approaches infinity is sandwiched between the functions 1 over x and negative 1 over x. So let's take a look at the graph. Sorry, I didn't mean for that to be on top of it. But look what happens here on the right. It goes up and down. It oscillates positive, negative, positive, negative. But each oscillation gets closer and closer to the x-axis. And we would expect that the horizontal asymptote of 1 over x would be 0. And so we find graphically the same thing happens. So we can say that the function oscillates about the x-axis. But we know that it's always stuck between negative 1 over x, which has an asymptote at 0, and 1 over x, which has an asymptote at 0. So we can say that this function, because it's stuck between those two, also has a horizontal asymptote. And this is probably the first time that we've seen a horizontal asymptote that fluctuates. It goes up and down and crosses the asymptote an infinite number of times. But every time it crosses and goes above or crosses and goes below, it gets closer and closer to 0. So some properties of limits. The limit, if L, M, and K are real numbers, and the limit of f of x is L, and the limit of g of x is m, then the limit of f of x plus g of x is the sum of the limits. The limit of the sums is the sum of the limits. The difference of the functions is the difference of the limits. Same thing with product. These should be dots. I don't know why they're coming through as boxes. And the constant multiple, if we multiply a function by k, we can also just multiply its limit by k. Quotient rule, if we divide two functions, we can divide their limits as long as the limit of the denominator quotient is not 0. And the power rule, the limit of a function raised to a power is the same as the limit raised to that power. So those are our properties. And we've looked at limits as we go to infinity or go to negative infinity. Now what about limits as x approaches a value a? If the values of a function f of x outgrow all positive bounds as x approaches a finite number, we say that the limit as x approaches a is infinity. In other words, this is a vertical asymptote, and the function goes up and up and up, but never quite gets to a. The same is true if it becomes larger and approaches negative infinity. We also say that that is an infinite limit. So the line x equals a is a vertical asymptote of the graph of a function if either of these is true. If either the limit as we approach a from the right, and we'll talk more about this, or from the left, either goes straight up or straight down. So let me draw a picture again. Let me put my a back in here. So the limit as we approach a from the right, in other words from the positive part of the graph, if my function is approaching a from the right-hand side, in the picture that I've drawn, the limit would be positive infinity. If we are approaching a from the left-hand side, in this case, it would be negative infinity. So this would be the limit as x approaches a from the right, and in the drawing that I have made, that would be affinity. And this would be the limit as x approaches a coming from the left-hand side, and that would be negative infinity. We're going to talk about the fact that in this case, the limit as x approaches a, which would imply from either side, does not exist. DNE. I ran out of room there. Okay, so we'll talk about that in a second. Find the vertical asymptotes of the graph that we're going to see below, and describe the behavior to the right and left of each vertical asymptote. So there's my function, and I want to be able to find my asymptotes. So let's first, I'm getting ahead of myself. So the vertical asymptotes come from setting the denominator equal to 0. In this case, 4 equals x squared, so x is plus or minus 2. So I'm going to draw a little picture over here. So plus 2, minus 2 are both vertical asymptotes. I think there's a picture that comes up in a minute. So the values of the function approach negative infinity to the left of negative 2. Let me keep going and see if I can get that graph to pop up. There it is. Okay, so as we approach negative 2 from the left, the limit as x approaches negative 2 from the left, that's this piece, from the left towards negative 2, goes down, so that is negative infinity. However, the limit as we approach negative 2 from the right, coming from the positive or right side of my graph, goes to positive infinity. Now let's look at what happens at x equals 2. The limit as x approaches 2 from the left, again from the negative side coming towards 2, that would be this piece, is positive infinity. And the limit as x approaches 2 from the right, coming from the right towards positive 2, is negative infinity. So I have 4 different limits here. Therefore, the vertical asymptotes are negative 2 and 2, and we found that earlier algebraically. So, the function g is a right end behavior model for f if and only if f of x over g of x equals positive 1. The left end behavior model for f if and only if this quotient also approaches 1. So if the top and the bottom both approach the same value, then g of x is a right end behavior model. Now what are we talking about? So if I have a function like the one I just had, whoops, did not mean to lose that slide. Okay, so like the one I just had, and it did, oh, I don't remember which way it went on the right. Let me go back. It went down on the right. Okay. There we go. So it did this over here. So if I can find a function, and we're talking about end behavior this time, so in this case it comes up here along to 0. If I can find a simple function that mirrors this end behavior, in other words, when we get way out here to the right, f of x and g of x are the same, then that is my end behavior model. So, end behavior models for polynomials. If one function provides both left and right end behavior, it is simply called an end behavior model. In general, g of x equals a to the n, a sub n times x to the n is an end behavior model for any polynomial function. In other words, we just have to look at the first term. Polynomials at their ends behave like monomials. So let's say we have f of x equals x squared plus 2x minus 3. And that function at the ends goes up and up. Our function g of x, just x squared, also goes up on the right and up on the left. So g of x is an end behavior model for this larger polynomial. Find an end behavior for this function. So we already said that the top is going to act like this and the bottom is going to act like this. Why does it do that? Because as we go towards infinity, this first term on the top and the first term on the bottom becomes so much bigger than these two values that those two don't make much difference. If I put 1,000,000 in for x squared, this plus 7 isn't going to make any difference in my behavior. It's going to be so small as to be negligible. So 3x squared is an end behavior model for the numerator, 4x squared is one for the denominator, therefore 3/4 is an end behavior model, and this function, if we graphed it, would have a horizontal asymptote at 3/4, and whether it approached from the top or the bottom, it's going to still approach that value of y equals 3/4, and it's going to do it on this end as well. Now a whole lot of stuff might happen in between, but all we care about is that it's going to approach that line from the left and the right, either the top or the bottom, I don't know which until I graph it, and so this is my end behavior. So in this example, the end behavior model for y equals 3/4 is also a horizontal asymptote of the graph. We can use the end behavior of a rational function to identify horizontal asymptotes. A rational function always has a simple power function as an end behavior model. Okay, this is all for the notes. So if you need to go back and write anything down, please do. This point on, and I'm going to scroll through these slides for you, is a quick quiz. It's just got a couple of questions. Each slide will have a question. The slide after it will have the answer. If you want to take this now to see how you're doing, continue on with the video. If you don't, that's fine. You can end now, but do know that at a later date, if you want to study for a quiz or a test, these quick quizzes are at the end of every couple of videos. So I'm just going to go ahead and scroll through. I'm not going to say anything. Pause if you want to attempt these questions. So pause now if you want to do the first question.